teach you an important topic called the mass moment of inertia, which is required for your dynamics problems as concerned to solve. Right. So let me share my active inspire board. So this is lecture number 35. Today's date is 12th May 2021. And today's topic of discussion is mass moment of inertia. So you know the definition of rigid body. So how do you define rigid body? A rigid body is the object which will not deform under the application of external load. The shape of the body remains same. You can also say rigid body is defined as under the action of external load, if the deformation is not zero, that is same as that of stating relative position of the particle forming the rigid body does not change. So that is what is rigid body. So the rigid body would have an important virtual property that is called mass. Its mass and its mass moment of inertia. So mass is going to act as an inertia for the expected translation of the body under the action of the load. Once it is overcome and then the body is acceleration under the acceleration motion, it is in the motion, then it is very difficult to stop the body motion. Again, that's because of its mass value. That is as far as translation is concerned. What do you mean by translation? A rigid body is moving from one point to the other, either in a straight line or in a curved path, is what is called a translation. The resistance that would be offered for any rigid body to start its motion or to stop its motion is influenced by the mass value of the body. Similarly, you would also see in dynamics there is another important effect of action of forces on bodies is what is called rotation. A flywheel mounted on a punching press is to rotate. A flywheel mounted on an axle of an engine is to rotate, store its energy. So the flywheel rotation is going to have an inertia to start its rotational motion or inertia to stop if it is already rotating state of motion. So that inertia is what is dictated by the property called mass moment of inertia. So the moment you say mass moment of inertia, what is that you should immediately get into your mind is rotation of body. Rotation of bodies. Rotation of bodies. Right? So the resistance offered to start the rotation or the resistance the rotating body to have to stop the motion is what is dictated by mass moment of inertia. Or you can see that element would appear in a governing equation of motion of rotation given by Euler equation. Unbalanced moment present in a body would cause its rotation I into alpha, where this I is what is called mass moment of inertia. So unless and until you know mass moment of inertia of a rotating body about the axis of rotation, you would not be able to calculate a motion parameter called angular acceleration. This is what is, it's not an angular, it's not simply linear, it's angular acceleration. Which is important to find out to describe the motion geometry of rotating bodies. We require this mass moment of inertia, which is analogous like the other way we were looking at. If any unbalanced force present in the body because of action of forces, that would cause mass times acceleration, effect force. This is called an effect force in the body, and the body will accelerate in the direction of an unbalanced resultant. So that is what is Newton's second law, and this is what is called an Euler equation. You see here, the role of mass is the resistance for translation. For translation. If I say this MA is brought on the other side and I say it's D'Alembert's force, our mass is what is important, times acceleration is what is the effect force, you can say, for the moving bodies. So to stop the moving body or to start the moving body to move, the resistance offered is by mass, whereas analogous way, if you are looking at to start the rotation or to stop the rotating body motion, the resistance offered is what is by mass moment of inertia. So how do you represent that mathematically is what, let us first look at it. So for that, let us look at a rigid body. In mechanics textbook, it is customary that we represent the rigid body by drawing like a potato. So there is an axis now represented here, say this axis. About this axis, this body to rotate. How do I find out its mass moment of inertia? So let me describe this body is made of n number of masses, dm1, dm2, dm3, and so on like that. And this distances from here is r1, r2, this is r3, and so on. So how do you represent that is, if I consider an elemental mass dm at a distance r, we consider an elemental mass dm at the distance r, this is simply dm. Like that, so many number of masses are there that forms this rigid mass, rigid body. Then I would define my rotational inertia about this axis. Say this axis is AA axis. IAA would be defined as integral r squared dm. This is mathematical definition of mass moment of inertia about the rotating axis. And this quantity would be equivalent to k square into m, where this k is called, or this k is called here, is radius of gyration. Radius of gyration. So when I put this, what does that meaning? It is equivalent. Having this entire rigid body mass is represented with respect to this axis A at a distance k by a lumped mass, a concentrated mass. This is mass m. So the entire mass m here of this body is kept now at a distance km. So this k square into m is what is IAA is given mathematically by this definition, integral r square dm, or it is k squared m. Right? This is not dm, it is total mass concentrated at a distance k. Then k squared into m is what is equivalent to what I get from this integral. So this is mass moment of inertia. So you can also look at this an interesting way with respect to different axes of rotation. I had an arbitrary axis of rotation to start its definition, but you can also look at now a rigid body. This rigid body is now defined with respect to x, y, z. So I have this. So with respect to this rigid body is defined now with respect to point O, and I have an elemental mass here. Say this is now not, it's an elemental mass dm, and it is oriented at a distance x, y, z coordinate. So the coordinate of this is say x comma y comma z. So how do I represent? So x is distance along x axis, and distance along y axis, and distance along z axis. So I would get that distances like this. If this is my x axis, I would get those distances like this. So I will have to move along x axis and then y axis and then z axis. So let me take this position. Y distance is somewhat here, and then this is how I represent. Now this distance is x, and this distance is y, and this distance is z. And this is my elemental mass of this rigid body with respect to origin O. So now you can also see that in XZ plane, I have this XZ and it's a square or rectangle. The diagonal of that is what is R. So now what is the definition of my mass moment of inertia about y-axis? I, y, when I write, what is that is the rotational inertia of this rigid body about y-axis, and that would be given by integral r squared dm, where this r here is given by Pythagoras theorem. R squared is x squared plus z squared. So it is going to be x squared plus z squared into dm. So look at now, I have a rigid body, and the rigid body has got a point O. With respect to point O, I have my Cartesian coordinate fixed at point O. Then the rotation of rigid body about y-axis is given by this. So it is going to be integral x squared plus y squared within bracket into dm. Right? Similarly, I can get what is my ix? That would be integral y squared plus z squared into dm. And iz would be integral x squared plus y squared into dm. So if the same is to rotate about x-axis, then you have to consider now a rectangular box here like this. In this now about x-axis, now this become r. This is the perpendicular distance. So this is perpendicular distance of dm. So here I have this is a rectangle where y squared plus z squared that comes here for this. Similarly, to get about a z-axis, I have to finish this box construction. So now you look at this distance is what is perpendicular distance r, which is given by x and y. That is how this comes. So this is how you should understand mathematical definition of rigid body. It's the rotational components along x, y, z axis. If it is rotating about a particular axis, but I have to get its rotation about x axis, y axis, z axis, I would get through this formula, right? So here also, like you have a parallel axis theorem for area moment of inertia, here also you have parallel axis theorem holds good. So that you can understand with this diagram. So let's again look at a rigid body. So I know with respect to these axes set, this is my x, y, z axis, right? Z axis. The CG location of this rigid body, say somewhere here. This is CG location. And I have here an axis set, which is x dash, y dash, and z dash. So now the CG location, how is it located? It would be given with respect to x, y, z coordinate, x bar, y bar, and z bar. Now let me consider an elemental mass dm somewhere on this rigid body, and its coordinate with respect to small x, small y, small z is x comma y comma z, where x is x bar plus x dash, y is y bar plus y dash, z is z bar plus y dash. Right? I can define like this. So now, what is the definition now? Ix, if I need, it is integral y squared plus z squared into dm. So if I substitute in that y as y bar plus y dash square plus z as z bar plus z dash square into dm, I would have now this is going to be y bar square dm plus y dash square dm plus 2y bar y dash into dm is all integral, right? Plus z bar square dm plus z dash square dm plus 2 into z bar into z dash into dm, right? So this is all individual integral, or I can take this dm out and I have one integral outside. So now in this you see that first moment of mass about central axis is 0. So that this term is going to be 0. Similarly, this term is going to be 0. So what is that I have left with? I have left with y bar square plus z bar square into dm plus integral y dash square plus z dash square into dm is what is ix. So what is y bar square plus z bar square dm? This distances are of the CG location. So I have now this is definition. This is going to be like this. So mass times I have to take this is integral. See, these are fixed constant for the rigid body. Y bar and Z bar distance are fixed because it's a centroidal location, and this distance square will not vary. Only y dash and z dash would be varying. So I would have integral dm is become m into y bar square plus z bar square plus here it is ix dash is what is this? So y dash square plus z dash square within bracket into dm is ix dash is what is ix. So these all are mass moment of inertia now. So mass moment of inertia about an arbitrary axis set x, y, z, which is not a centroidal axis set, then see here you see x axis is not a centroidal axis. X dash axis is a centroidal axis. So what is that you understand? If I have to get a rotation of a rigid body about an axis which is not its centroidal axis, that would be obtained through this. So about the centroidal axis, what is its mass moment of inertia plus this. So here this y dash square plus z dash square would be r bar square, right? So this is what is called the parallel axis theorem here. What we have seen in case of area moment of inertia, similarly, where there we had the area, whereas here it is mass. And see, similarly, you can also have Iy is given by, you would say that it is mass into x bar square plus z bar square plus Iy dash. And Iz would be mass into y bar square plus z bar square, sorry, x bar square x bar square plus Iz dash. So this is the definition that one can understand. Now let us look at a simple case. Instead of a rigid body, I'm going to take now a square plate.